Electrical resistance turns a significant portion of our power current into waste heat. To build a grid that moves charge without loss, we have to change the physics of the conductor itself. For over a century, the only solution has been extreme refrigeration. We rely on liquid nitrogen and helium to suppress the thermal energy that disrupts the superconducting state. The standard model assumes that heat is the primary enemy. At high temperatures, atomic vibrations are thought to shatter the quantum Cooper pairs that allow for frictionless flow. But ultra-thin films prove this model is incomplete. As these materials approach absolute zero, where heat is almost entirely absent, they can suddenly collapse, transitioning from a superconductor into a rigid insulator. If heat were the only variable, the condensate should become more stable as we approach zero. Instead, it reaches a breaking point. The ODTOE framework suggests we have been focusing on the wrong metric. Temperature is just one proxy for a much larger threat. The true governing axis is the total decoherence rate, a sum of destruction that includes structural disorder and quantum phase fluctuations alongside thermal energy. Cooling is a brute force method of closing a single decoherence channel. This implies that room temperature superconductivity is not a thermodynamic impossibility, but a challenge of material architecture. To manage this architecture, the model relies on a core postulate, the balance inequality. On one side, the decoherence rate presses down, the combined pressure of thermal vibrations, defects, and quantum noise. On the other side is the restoration rate, the material's capacity to repair its quantum state. The superconducting state remains stable only when restoration mathematically outruns destruction. Failure to reach this balance results in phantom coherence. Here, a material can possess the raw Cooper pairs, the amplitude, without the long-range phase coherence needed to bind them together. This explains the recent history of retracted claims, including the LK99 report. Researchers detected the signatures of electronic pairs, but could not find the phase-coherent Meissner effect required for true superconductivity. The presence of the pairs is only a starting point. The material must still satisfy the balance inequality to sustain a macroscopic state. Using the ODTOE framework, we can move from accidental discovery to active engineering, shielding the condensate along 4 distinct material roads. The first road involves increasing the energy gap, the anchor. By raising the energy required to break electronic pairs, we increase the threshold for thermal decoherence, as seen in hydrides under extreme pressure. The second road utilizes phase stiffness and quantum geometry. This allows a material to maintain order even when electron kinetic energy vanishes, a phenomenon recently measured in magic-angle twisted bilayer graphene. The third road targets the decoherence rate itself. By placing the system in protected subspaces or incommensurable lattices, we isolate the condensate from the resonant noise that would otherwise destroy it. Finally, the fourth road uses network topology. By engineering the percolation of coherent islands, we build structural resilience directly into the material's microscopic web. Activating these 4 pathways simultaneously allows us to firmly lock down non-thermal decoherence without depending on extreme cold. Fortifying the material against quantum and disorder fluctuations naturally extends the range of the thermal channel toward ambient temperatures. This provides a rigorous control model with testable, falsifiable predictions that are currently being prepared for laboratory verification. It defines boundary conditions of stability, mapping out the inversion line where material anchors and phase stiffness shift. A key test involves measuring a scaling exponent. If the data matches predictions, we mathematically distinguish a true stable state from a phantom. The third law of thermodynamics makes absolute zero a physical asymptote, a limit that can be approached but never actually reached. It closes the thermal channel, but it isn't the only way to protect the condensate. Stability is a function of internal material architecture, not just the temperature of the room. If these models are verified, our focus shifts. We stop hunting for rare compounds and start building them. We actively engineer the conditions for discovery.